What if I told you there's a place in the universe where reality itself unravels, where time doesn't flow, it shatters, where space doesn't curve, it fractures into infinite possibilities? This isn't science fiction. This is the heart of a black hole, where Einstein's theory of relativity collides head-on with the mind-bending weirdness of quantum mechanics. And what happens in that collision? It's not just a scientific curiosity, it's a cosmic revolution waiting to be understood. Think about the strangest thing you've ever encountered, maybe a magic trick that left you baffled or a dream so vivid it felt real. Now multiply that by infinity, and you're still only scratching the surface of what happens when quantum superposition meets the crushing gravity of a black hole. Particles existing in multiple states at once, time loops folding in on themselves, information disappearing. Or is it? For decades, physicists have grappled with these questions, but the answers we're uncovering now are more astonishing than anyone predicted. This isn't just about equations or abstract theories. It's about the very fabric of existence. Every black hole is a laboratory for the most extreme physics imaginable, and the implications ripple across our understanding of everything from the birth of the universe to the nature of consciousness itself. Today, we're going to explore 30 of the most startling, unseen consequences of this quantum relativity clash. Some will challenge your intuition. Others might rewrite what you thought was possible, and by the end, you'll see the universe and maybe even reality in a whole new light, so buckle up. We're diving deep into the unknown. Here's the mind-bending twist physicists never saw coming. Black holes might not erase information at all. Instead, they could be storing it in the most bizarre way possible. Quantum superpositions. Picture this: you drop a book into a black hole. According to Einstein's relativity, it's gone forever, crushed into oblivion. But quantum mechanics whispers something far stranger. That book's information might not vanish. It could be scrambled, stretched, and imprinted onto the very fabric of the event horizon, like a cosmic fingerprint hidden in the quantum noise. This is the heart of the quantum information paradox, a puzzle that's haunted scientists for decades. Stephen Hawking once thought black holes were the ultimate shredders, permanently destroying anything that fell in. But if quantum superposition is real, if particles can exist in multiple states at once, then information might never truly disappear. It just transforms, entangled in a web of possibilities at the edge of spacetime. Imagine a hard drive so advanced it doesn't just store data, it stores every possible version of that data simultaneously. That's the kind of quantum magic we're talking about. The stakes couldn't be higher. If information isn't lost, it changes everything we know about entropy, causality, even the fate of the universe. Some theorists, like Leonard Susskind, argue black holes obey a holographic principle where all the information inside is somehow projected onto their two-dimensional surfaces. It's as if the universe has a built-in backup system, ensuring nothing is ever truly lost. But how? The answer might lie in the strange dance between quantum entanglement and gravity, where particles at the event horizon become quantum mirrors, reflecting data we once thought was gone forever. This isn't just theoretical gymnastics. If black holes preserve information, it means the universe has a kind of quantum memory, a hidden ledger keeping track of every star, every planet, every atom that's ever crossed the event horizon. And that raises an even wilder question. If information can survive a black hole, what else can? Could the universe itself be encoding its history in ways we're only beginning to glimpse? The implications ripple far beyond astrophysics, touching the very nature of reality, time, and whether anything in the cosmos is ever truly lost. At the very edge of a black hole, where gravity stretches the fabric of reality to its limits, space-time doesn't behave like the smooth, unbroken surface Einstein envisioned. Instead, it seethes, it churns, it becomes a boiling quantum foam, a chaotic storm of microscopic fluctuations where space and time lose all semblance of order. Picture the surface of the ocean during a hurricane, but instead of water, it's the very structure of the universe itself, fracturing into fleeting bubbles of alternate dimensions and probabilities. This is space-time foam, a concept so radical it forces us to rewrite our understanding of reality itself. John Wheeler, the visionary physicist who coined the term black hole, first proposed this idea decades ago. He imagined space-time not as a pristine sheet but as a frenetic quantum froth at the smallest scales. Near a black hole's event horizon, where gravity warps space-time beyond recognition, this foam isn't just theoretical, it might be the key to unlocking hidden layers of the cosmos. Think of it like static on an old television screen, but instead of random noise, those flickering pixels are entire universes flickering in and out of existence. Some theories suggest these quantum bubbles could be wormholes, tiny tunnels connecting distant parts of space, or even different dimensions altogether. But here's where it gets even stranger. If space-time is foamy, then black holes aren't just cosmic vacuum cleaners. They're quantum blenders, churning the very rules of physics into something unrecognizable. Particles popping in and out of existence, dimensions folding like origami, causality itself unraveling. This isn't just a challenge to Einstein's relativity, it's a full-scale rebellion. Modern quantum gravity models like loop quantum gravity and string theory are now racing to map this chaos. Some predict that the foam's turbulence could leave detectable imprints, subtle ripples in space-time that might one day be spotted by advanced gravitational wave observatories. What does this mean for us? If space-time foam is real, then black holes might be more than just celestial oddities. They could be portals, revealing the deeper, wilder structure of the universe. Imagine dipping a cup into this quantum sea and pulling out a handful of reality itself, only to find it's nothing like what we thought. It's a reminder that the cosmos is far weirder, far more dynamic than our textbooks ever dared to suggest. And if we can decode the secrets of this foam, we might finally bridge the gap between quantum mechanics and gravity, unlocking the universe's ultimate blueprint. Time doesn't just slow near a black hole, it fractures. Einstein showed us how gravity stretches time like taffy, making seconds crawl compared to the outside universe. But throw quantum mechanics into the mix, and time doesn't just bend, it splits into parallel possibilities. Imagine standing at the edge of a black hole's event horizon, watching your wristwatch tick slower and slower, while quantum particles around you flicker between existing and not existing, between past and future, between moments that haven't happened yet and ones that already did. This is where relativity's orderly clockwork collides with quantum chaos, creating a reality where time itself becomes a tangled web of maybes. Atomic clocks aboard GPS satellites already prove time warp is real. They tick ever so slightly faster in Earth's weaker gravity than clocks on the ground. But near a black hole, this effect isn't just a tiny adjustment. It's an existential crisis for causality. Quantum particles refuse to pick a single state until observed, meaning time for them isn't a straight line, it's a haze of probabilities. Now picture that uncertainty scaled up to cosmic proportions. What if entire chunks of space-time inside a black hole exist in superposition, with time flowing forward, backward, and sideways all at once? Some theories suggest the singularity isn't a point but a quantum smear, where now loses all meaning. This isn't just philosophy. If time can exist in superposition, it rewrites the rules of cause and effect. Normally, relativity keeps the universe's timeline tidy. Causes come before effects, eggs crack before they're scrambled. But in the quantum realm, particles routinely defy this order. Entangled particles influence each other instantly across vast distances, as if time and space don't apply. Near a black hole, these quantum quirks could scale up dramatically. The past might influence the future while the future loops back to alter the past, a hall of mirrors where before and after blur into a single, swirling paradox. The wildest implication, if time inside a black hole is truly fluid, it might not be a one-way trip to destruction. Some models hint that singularities could be gateways to other timelines or universes, where the arrow of time points in entirely new directions. Picture a river forking into countless streams, each carrying its own version of history. This would mean black holes aren't just cosmic dead ends, they're time machines, weaving threads of possibility into the fabric of the multiverse. And if that's true, the universe isn't just stranger than we imagined. It's stranger than we can imagine, with every black hole a ticking, twisting quantum clock at the heart of reality itself. What if the secret to interstellar travel has been hiding in plain sight, not as a fixed tunnel through space, but as a flickering quantum mirage? Wormholes, those legendary shortcuts across the cosmos, might not be the stable, predictable passageways science fiction promised. Instead, they could be ghostly bridges woven from the same quantum uncertainty that governs particles at the smallest scales. Imagine a subway system where tunnels appear and vanish at random, where stations shift locations based on probability. That's the bizarre reality emerging from the marriage of quantum mechanics and black hole physics. Einstein and Rosen first theorized wormholes as static bridges connecting distant points in spacetime, but modern physics paints a far wilder picture. These cosmic shortcuts could be dynamic superpositions, here one moment, gone the next, existing in multiple states simultaneously until something or someone interacts with them. Picture a doorway that's both open and closed until you reach for the knob. Juan Maldacena and others now suggest that entangled particles, those spooky twins of quantum physics, might act as cosmic glue, briefly stabilizing these wormholes just long enough for them to function. It's as if the universe is constantly knitting together threads of space-time, only for them to unravel microseconds later. The implications are dizzying. If black holes can form quantum bridges with white holes, their theoretical opposites, spewing matter rather than consuming it, then every black hole might be a potential stargate. Some models even suggest these tunnels could connect not just distant regions of our universe, but entirely separate universes within the multiverse. Forget warp drives. The real interstellar highway might be a network of quantum fluctuations, blinking in and out of existence like fireflies in the cosmic dark. The catch, navigating such a route would be like surfing a tsunami blindfolded. One wrong move, and you might emerge in a reality where time flows backward or the laws of physics are unrecognizable. Yet the most tantalizing possibility isn't just travel, it's communication. If entangled particles can stabilize wormholes, could we harness them to send information across galactic distances instantaneously? Quantum entanglement already allows particles to influence each other faster than light. Scale that up to a wormhole, and you've got a cosmic telegraph system, transmitting data through the quantum foam itself. Of course, the energy required would dwarf anything humanity has ever produced. But in a universe where black holes twist the rules daily, who's to say what's truly impossible? The only certainty is this: if wormholes are quantum superpositions, then the universe is far more interconnected, far more dynamic than we ever dreamed. And the greatest adventures might lie not in the stars, but in the spaces between, where reality flickers like a candle in the wind. Black holes might seem like the ultimate vaults, locking away everything that falls in, but what if they're secretly leaking their contents, one quantum particle at a time? Stephen Hawking's most revolutionary idea was that black holes aren't completely black. They emit radiation, slowly evaporating over eons. But here's the twist. Every particle of this Hawking radiation could be quantumly entangled with its doomed counterpart still trapped inside the black hole. It's as if the universe stitched them together with invisible threads, linking the inside and outside in a bizarre, intimate dance. This creates a paradox that's kept physicists awake for decades. If Hawking radiation is truly random, how can it possibly carry any information about what fell into the black hole? Randomness implies chaos, yet quantum entanglement demands perfect correlation. The resolution might lie in superposition, the idea that particles exist in multiple states simultaneously until measured. Imagine a book burning to ashes, but instead of losing the story, every escaping smoke particle holds a scrambled fragment of the text. Now amplify that to a cosmic scale. The black hole isn't just spewing random energy, it's emitting a quantum-encoded message, piece by piece, with each particle hovering in a haze of possibilities until it's observed. The implications for entropy, the universe's measure of disorder, are staggering. Normally, entropy only increases like a shattered glass never reassembling itself. But if Hawking radiation carries hidden information, then black holes might be playing a quantum shell game with entropy, shuffling it around rather than destroying it. Some theories suggest the event horizon acts like a holographic screen, projecting information outward even as the black hole devours matter. Picture a scrambled television signal that, when analyzed just right, reveals a perfect image. The randomness isn't random at all. It's a disguise, a cosmic sleight of hand where superposition preserves the rules of physics in ways we're only beginning to decode. This reshapes our understanding of black holes from cosmic trash compactors to intricate quantum archivists. They might not obliterate information, they transform it, stretch it, and broadcast it back into the universe in a language we're still learning to read. And if that's true, then the universe has a far more sophisticated recycling system than we ever imagined, one where nothing is ever truly lost, just rewritten in the strange, shimmering code of quantum superposition. Entropy has always been the universe's strict accountant, keeping track of every bit of disorder with unrelenting precision. The second law of thermodynamics insists it can only grow, like an unstoppable tide of chaos erasing every trace of order. But black holes laugh in the face of this cosmic rulebook. Here, where quantum superposition twists reality into knots, entropy doesn't just increase, it performs a symphony, a delicate dance of information that defies everything we thought we knew. Picture a library engulfed in flames. In the classical view, the books burn to ash, their stories lost forever. But in the quantum realm, the information doesn't vanish, it transforms. The holographic principle suggests that every bit of data swallowed by a black hole isn't destroyed. Instead, it's meticulously encoded on the event horizon's surface, like an intricate fractal tattoo etched into spacetime itself. Each particle, each atom, leaves a ghostly imprint in this quantum ledger, preserved in a state of superposition where past and present coexist. It's as if the universe has a failsafe, a backup drive written in the language of entanglement and probability. This isn't just a tweak to the rules, it's a revolution. Normally, entropy means irretrievable loss, like scrambling an egg and never being able to unscramble it. But black holes might be playing a different game. They don't erase, they rearrange, storing information in ways so subtle we're only beginning to decode them. Leonard Susskind and Gerard T. Hooft proposed that the event horizon acts like a quantum hard drive. with every falling object's data compressed into two-dimensional pixels. Imagine a cosmic zip file where the contents are stretched, twisted, and folded but never truly deleted. The implications ripple far beyond astrophysics. If entropy isn't absolute, if information can be preserved against all odds, what does that mean for the fate of the universe? Could the arrow of time itself be more flexible than we thought? Some theories even suggest that black holes might eventually replay their stored data, like a cosmic projector flickering to life long after the film was fed into the fire. It's a haunting thought that somewhere in the quantum static of a dying black hole's hawking radiation, the echoes of long-lost stars might still whisper. And here's the kicker. This quantum symphony of entropy might hold the key to unifying relativity and quantum mechanics. If black holes can balance the books keeping track of every bit of information while still obeying the laws of thermodynamics, then they're not just cosmic oddities. They're masterpieces of quantum engineering, proof that the universe operates with a hidden elegance we're only starting to glimpse. So the next time you hear that entropy always wins, remember, black holes are out there rewriting the score. The singularity at the heart of a black hole has long been described as a point of infinite density, a place where the laws of physics break down completely. But what if that terrifying endpoint isn't a point at all? Quantum mechanics paints a radically different picture. A fuzzy, shimmering cloud of probabilities where the very idea of location loses meaning. Instead of a single, crushing dot, the core of a black hole might be a smeared-out quantum storm, a place where gravity and uncertainty twist together into something entirely new. Loop quantum gravity, one of the leading theories trying to unite relativity with quantum mechanics, suggests gravity has a built-in limit like a cosmic safety valve preventing infinite collapse. At a certain threshold, matter doesn't just keep squeezing smaller, it rebounds. Imagine a rubber band stretched to its limit, then snapping back with a jolt. In this model, the singularity isn't the end, it's a quantum bounce, a moment where collapse flips into expansion. Some theorists, like Abhay Ashtekar, propose this could birth an entirely new universe inside the black hole, a hidden cosmos budding from the wreckage of the old one. This turns the traditional view of black holes upside down. Instead of a one-way trip to destruction, crossing the event horizon might be a transition, a doorway to something stranger. Picture a tunnel where space and time don't just bend, they shatter into fragments, reassembling into new configurations on the other side. The point of no return becomes a quantum roulette wheel spinning with possibilities. Some paths might lead to new dimensions, others might loop back into our own universe in unpredictable ways. It's as if every black hole contains a cosmic dice roll, with reality itself as the prize. The implications for cosmology are staggering. If singularities are quantum probability clouds rather than dead ends, then black holes could be the universe's recycling centers, devouring old stars and birthing new realities in their depths. Our entire cosmos might even owe its existence to such a bounce, a rebound from some ancient collapse we can't yet fathom. And if that's true, then the night sky isn't just studded with traps, it's dotted with potential genesis points, each black hole a cradle for universes we'll never see. The singularity wasn't the end of physics after all. It was just the beginning of a story we're only starting to read. At the precipice of a black hole's event horizon, quantum particles face an existential tug of war. Gravity's crushing pull should shred their delicate superpositions, collapsing them into definite states, like a house of cards flattened by a hurricane. Yet something extraordinary happens. Instead of surrendering to chaos, these particles cling to their quantum coherence, dancing on the edge of annihilation like tightrope walkers defying a storm. This defiance of decoherence isn't just theoretical, it's been glimpsed in laboratories right here on Earth. Take Bose-Einstein condensates, clouds of atoms chilled to near absolute zero where quantum behavior becomes visible to the naked eye. In these fragile states, particles move in perfect unison, forming a single quantum wave. When subjected to extreme conditions like rapid acceleration or intense magnetic fields, they don't immediately decohere. Instead, they resist, adapting in ways that mirror what might occur near a black hole's event horizon. It's as if quantum systems have an innate survival instinct, finding loopholes in the laws of physics to preserve their coherence against all odds. This cosmic balancing act hints at something revolutionary. If black holes don't just destroy quantum information but process it, if their extreme environments act like natural supercomputers, then the universe might be performing calculations we can't even fathom. Imagine a quantum computer the size of a star, where entangled particles perform operations at scales that make our most advanced silicon chips look like abacuses. Some theories suggest the event horizon's chaotic surface could function like a quantum circuit, with particles tunneling in and out of existence acting as logic gates. The inputs, everything that ever fell into the black hole. The output, a cosmic transformation we're only beginning to decode. What makes this idea so tantalizing is its implications for information processing. In our labs, maintaining quantum coherence is a constant battle against noise and interference. But black holes might have mastered this challenge, leveraging their extreme gravity to stabilize superpositions in ways we can't yet replicate. It's like discovering nature invented the perfect quantum hard drive billions of years before humans even conceived of binary code. The catch: accessing that computational power would require surviving conditions that liquefy atoms. Yet the parallels are too striking to ignore. Just as quantum computers exploit superposition to solve problems intractable for classical systems, black holes might be performing their own unfathomable calculations. Some researchers speculate these cosmic processors could even generate new physical laws in their depths, algorithms written in the language of spacetime itself. If that's true, then black holes aren't just gravitational monsters. They're the universe's original programmers running codes we're only now learning to read. And somewhere in that quantum turbulence, the answers to physics' greatest mysteries might already exist waiting for us to catch up. Black holes don't just consume matter, they might be crunching numbers on a cosmic scale. Think of the most powerful supercomputer ever built, then multiply its processing power by infinity. That's the staggering possibility emerging from the quantum chaos at a black hole's core. Seth Lloyd, a pioneer in quantum computing, proposed that the universe itself could be a vast computational engine, with black holes acting as its processors. Every particle falling past the event horizon isn't just lost, it's transformed into a variable in an equation we're only beginning to decipher. Picture a chessboard where every square is a universe and every move calculates a new reality. That's the kind of parallel processing black holes might perform. Unlike classical computers that solve problems step by step, quantum systems explore all possible solutions simultaneously through superposition. Now imagine that scaled up to astrophysical proportions. A black hole's singularity isn't a dead end but a quantum core executing calculations across countless superimposed states. The holographic principle takes this further, suggesting the entire cosmos might be a projection of information processed on some distant boundary, with black holes as its quantum circuit boards. Here's where it gets surreal. If black holes compute, what kind of problems are they solving? Some theorists speculate they could be simulating alternate timelines or testing the laws of physics in ways our laboratories never could. Just as weather models predict storms by crunching atmospheric data, black holes might explore gravitational extremes by running quantum algorithms in their cores. Their answers could be written in the fabric of spacetime itself, encoded in the spin of particles, the curvature of gravity, even the expansion rate of the universe. We might already be living inside the output of these cosmic computations without realizing it. This raises a profound question. If the universe is a self-simulating system, are black holes its way of stress-testing reality? The way a programmer runs diagnostics on a server, these gravitational behemoths could be probing the limits of physical laws, tweaking variables in their quantum superposition to see what holds. Every collapsing star might birth a new experiment, a pocket of spacetime where matter, energy, and information interact in ways that push the boundaries of the possible. And if that's true, then the cosmos isn't just governed by physics, it's actively exploring them, with black holes as its most daring laboratories. The implications ripple beyond astrophysics. If nature harnesses quantum superposition for computation, it suggests an underlying order to the chaos, a hidden logic woven into the fabric of existence. Our own quantum computers struggle with decoherence, their fragile states collapsing before complex calculations finish. But black holes, with their immense gravity and quantum turbulence, might have evolved workarounds we haven't discovered yet. They could be the universe's original programmers, running codes written in the language of entanglement and spacetime. And somewhere in their depths, the answers to existence itself might be flickering in and out of superposition, waiting to be decoded. Quantum mechanics tells us reality solidifies only when observed, but inside a black hole, where no light escapes and no signal returns, who does the observing? This isn't just a philosophical puzzle, it's a cosmic glitch in the fabric of existence. On Earth, the observer effect is straightforward. A particle's wave function collapses when measured, snapping from fuzzy probability to definite state. But in the abyss of a black hole, the rules shatter. There's no lab, no scientist, no apparatus to force quantum possibilities into concrete reality. So what happens to superposition when the universe itself looks away? Some theories suggest black holes are nature's blind spots, regions where quantum states never fully resolve. Imagine a room where every light switch is stuck halfway between on and off, frozen in uncertainty. Now scale that to a singularity. Particles inside might exist in eternal limbo, suspended between states because nothing can observe them into existence. This could explain why dark matter, which outweighs visible matter 5-to-1, remains invisible. Its particles aren't just hiding, they're fundamentally unresolved, caught in quantum purgatory. The very darkness of black holes might be a clue that reality, when left unwitnessed, stays fluid. Yet other physicists propose a wilder answer. The universe itself acts as the ultimate observer. Just as a tree falling in an empty forest still creates sound waves, a black hole's interior might be observed by the fabric of spacetime beyond its event horizon. The holographic principle supports this. If information inside a black hole is mirrored on its surface, then the boundary becomes a cosmic measuring device, collapsing superpositions by proxy. It's like a surveillance system where the walls themselves record reality, ensuring no quantum state goes unaccounted for. This leads to an unsettling possibility. If observation defines reality and black holes challenge observation's limits, could consciousness play a role in cosmic physics? Some interpretations of quantum mechanics, like von Neumann-Wigner's consciousness causes collapse, suggest mind and matter are entangled at the deepest level. While controversial, the idea gains eerie traction when considering black holes. Are these gravitational monsters proof that reality, at its core, requires a witness? Or are they cosmic exceptions, pockets where the universe lets its hair down and stops keeping score? The implications stretch beyond theory. If black holes are regions where observation fails, they might be generating dark matter as a byproduct, particles forever half real, half ghost. Alternatively, if the universe enforces quantum resolution even in the void, it implies a hidden order governing existence, a rule book we've only glimpsed. Either way, black holes aren't just crushing matter, they're crushing our assumptions about how reality works. And in that collapse, whether observed or not, lies a truth far stranger than fiction. Dark matter has always been the universe's most persistent ghost, felt but never seen, shaping galaxies with invisible hands. But what if we've been searching in the wrong dimension? The answer might not lie in undiscovered particles, but in the quantum shadows cast by black holes. Picture this: every particle teetering on the edge of a black hole's event horizon exists in superposition, its position and momentum blurred across probabilities. While we can't observe these quantum states directly, their gravitational fingerprints could linger like cosmic echoes, warping spacetime in ways that perfectly match dark matter's elusive effects. This isn't just poetic speculation. Quantum field theory suggests that particles in superposition still interact gravitationally with their environment. They're enough to bend light and tug stars. Even if they're not, they're enough to collide with detectors. Near a black hole where spacetime churns with quantum turbulence, these half-real particles could accumulate like fog around a street lamp. Their combined gravity would explain why galaxies rotate faster than visible matter predicts, why gravitational lensing reveals mass we can't see. It's as if the universe has been hiding its quantum ledger in plain sight, scribbled in the language of gravity rather than light. The implications are staggering. If dark matter arises from quantum superposition near black holes, it bridges two of physics' greatest puzzles with elegant symmetry. Suddenly, the hunt for exotic particles like WIMP or actions might be chasing phantoms. The real culprit could be the gravitational ripples of reality itself flickering in and out of existence. Experiments like LIGO, designed to detect spacetime ripples from colliding black holes, might already be gathering clues, those faint, unexplained signals in the noise. They could be whispers from the quantum fog, gravity waves from superpositions we've yet to decode. Even more tantalizing, this framework could rewrite galaxy formation. Supermassive black holes squat at the hearts of most galaxies, their event horizons swirling with quantum chaos. If their superposition residue generates dark matter's pull, then galaxies aren't just shaped by black holes, they're woven from their quantum uncertainties. Spiral arms, star clusters, even the cosmic web itself might be quantum fingerprints stretched across billions of light years. It's a cosmic dance where the invisible partner isn't a particle at all, but the unresolved potential of reality itself. The next time you gaze at the night sky, remember the darkness between stars might not be empty. It could be thrumming with quantum possibilities, a living testament to the universe's deepest mysteries playing out at the edge of black holes. And somewhere in that quantum haze, the answers to dark matter, and so much more might finally come into focus. Galaxies spin like cosmic whirlpools, their outer stars whipping around at speeds that should fling them into the void, yet something invisible holds them together. For decades, we've called that something dark matter, a mysterious substance outweighing visible stars 5-1. But what if the glue binding galaxies isn't matter at all? What if it's quantum entanglement stretched across light years by the supermassive black holes lurking at galactic hearts? Roger Penrose's controversial theories hint at this staggering possibility, that black holes aren't just destroyers but cosmic conductors, orchestrating quantum coherence on scales we once thought impossible. Picture a spiderweb glistening with morning dew, each droplet perfectly synchronized through subtle vibrations. Now replace the web with spacetime, the dew with entangled particles, and the spider with a black hole billions of times the sun's mass. That's the vision emerging from cutting-edge quantum gravity research. Supermassive black holes, with their unfathomable gravity and turbulent event horizons, could be acting as quantum tuning forks, forcing particles thousands of light years apart to vibrate in unison. This wouldn't just explain galaxy rotation curves, it would rewrite our understanding of how the universe organizes itself. The math behind this is as beautiful as it is bizarre. In standard physics, quantum entanglement decays with distance like a whisper fading in a storm. But black holes warp spacetime so severely that they might create quantum shortcuts, threads of coherence weaving through the galaxy's fabric like invisible stitching. Studies of quasars, the blazing cores of distant galaxies, reveal patterns that resemble interference, the hallmark of quantum behavior. If confirmed, this would mean stars on opposite sides of a galaxy aren't just neighbors, they're quantum collaborators, their motions choreographed by a black hole's gravitational ballet. Critics argue this stretches quantum theory beyond recognition. After all, maintaining coherence across such scales would require conditions as delicate as a snowflake surviving a supernova. Yet nature has a habit of surprising us. Recent lab experiments with Bose-Einstein condensates ultra-cold clouds of atoms behaving as single quantum entities show coherence can persist in unexpected ways. Scale that up to a galactic nucleus where magnetic fields and gravity interact in ways we're only beginning to model, and the impossible starts looking plausible. The implications ripple far beyond astrophysics. If galaxies are quantum coherent systems, then the universe operates more like a neural network than a collection of isolated objects, with black holes as its synapses, firing signals across the cosmic web. This could explain why galaxies cluster in filaments and voids, as if responding to some hidden resonance. It might even hint that consciousness itself, with its mysterious quantum underpinnings, is a tiny echo of a far grander phenomenon written into the fabric of spacetime. So the next time you gaze at the Milky Way's spiral arms, consider this. What looks like a whirlpool of stars might actually be a quantum symphony, its notes held together by the silent, unseen baton of a supermassive black hole. And if that's true, then the music of the spheres isn't just poetry, it's physics at its most profound. The birth of black holes might not require collapsing stars or cataclysmic collisions sometimes. All it takes is a quantum whisper. In the seething chaos of the early universe, mere moments after the Big Bang, space-time itself rippled with violent fluctuations. Under normal circumstances, these quantum tremors would flicker in and out of existence too quickly to matter. But in that primordial furnace where the entire cosmos was compressed into a space smaller than an atom, something extraordinary happened. Certain fluctuations didn't just vanish, they got stuck, frozen in place by the universe's rapid expansion. Like bubbles trapped in amber, these quantum hiccups might have grown dense enough to collapse into black holes, no star required. These wouldn't be the black holes we know today. Primordial black holes could be as small as a proton or as massive as a mountain, born from pure space-time turbulence rather than dying stars. And here's where quantum superposition plays the ultimate sleight of hand. Normally, quantum fluctuations resolve almost instantly, their uncertainty collapsing into nothingness. But in the early universe's extreme conditions, superposition could have stretched these fluctuations, sustaining them just long enough for gravity to take hold. Imagine a coin balanced perfectly on its edge, except instead of falling heads or tails, quantum physics keeps it teetering indefinitely until suddenly it transforms into a black hole. The hunt for these ancient relics is more than academic. If they exist, primordial black holes could solve two cosmic mysteries at once. Their gravitational pull might explain dark matter's invisible grip on galaxies, rendering exotic particles unnecessary. Or they could be lurking in our solar system's outskirts, their faint Hawking radiation betraying their presence as they slowly evaporate. Some theories even suggest these black holes could be ticking time bombs, their final moments unleashing energy bursts rivaling supernova. The key to finding them, looking for the impossible, gravitational lenses without visible mass, gamma-ray flashes with no apparent source, or stars that flicker as if something tiny but incredibly dense passed in front. Recent advancements are turning speculation into serious science. Gravitational wave detectors like LIGO might soon spot the ripples from colliding primordial black holes, while space telescopes scour the heavens for telltale evaporation signatures. Even more intriguing, some models suggest these black holes could have formed in nested layers like Russian dolls, with smaller ones orbiting inside larger ones, all born from the same quantum instability. If confirmed, it would mean the universe is littered with black holes older than stars, relics of a time when reality itself was a quantum gamble. So the next time you hear that black holes come from dying stars, remember, the truth might be far stranger. Some could be quantum fossils, remnants of a cosmic lottery where the prize was existence itself. And if we find them, it won't just rewrite astronomy textbooks, it'll prove that the universe's wildest twists were written in the language of quantum uncertainty from the very beginning. Gravitational waves have already revolutionized astronomy, ripples in spacetime revealing colliding black holes and neutron stars like cosmic drumbeats across the universe. But buried in those signals might be something even more extraordinary, faint echoes, whispers of quantum mechanics warping gravity itself. When two black holes merge, their event horizons don't just combine smoothly, they shudder, vibrating like a bell struck by a hammer. According to classical physics, these vibrations should fade predictably, yet some researchers, like Nyayesha Shordy, claim the data shows anomalies tiny, repeating pulses that linger long after the main event. These could be the smoking gun of quantum gravity, superposition states snapping back into place like cosmic rubber bands. Imagine dropping two stones into a pond. The initial splashes are the gravitational waves we've detected, the violent merger of black holes, but quantum mechanics predicts there should also be subtle ripples rebounding from the fabric of spacetime itself, like echoes bouncing off hidden walls. These echoes would arise if the merged black hole's event horizon exists in a temporary superposition, a quantum blur between multiple possible shapes before settling into its final form. It's as if spacetime has memory, resisting the collapse until the last possible moment. The implications are staggering. This would be the first direct evidence that black holes obey quantum rules, bridging Einstein's gravity with the subatomic world. Critics argue these echoes could just be noise, artifacts in the data, but the timing is suspiciously precise. Quantum gravity theories predict echoes should appear at intervals tied to a black hole's mass, and that's exactly what some analyses of LIGO and Virgo data suggest. If confirmed, it would mean every black hole merger isn't just a collision, it's a quantum experiment on a cosmic scale, with spacetime itself as the lab bench. The echoes would encode information about the singularity's true nature, revealing whether it's a point, a ring, or something far stranger, like a fuzzball of tangled strings predicted by string theory. This isn't just academic curiosity. If spacetime remembers quantum states, even briefly, it challenges our most basic assumptions about reality. Normally, gravity smooths out quantum weirdness. What's fuzzy at small scales becomes definite at large ones. But black hole echoes suggest the reverse. quantum effects might scale up, leaving fingerprints visible across light years. Future gravitational wave detectors, like the space-based LISA mission, could settle the debate with unprecedented sensitivity. A confirmed echo would rank among the greatest discoveries in physics, proof that the universe plays by quantum rules even in its most extreme corners. So the next time you hear about colliding black holes, listen closely. Hidden in the chaos might be the faintest reverberations, a quantum hiccup echoing through spacetime, waiting to rewrite the laws of physics. Einstein pictured spacetime as a smooth, four-dimensional fabric, a cosmic stage where matter and energy performed. But what if that stage isn't fundamental? What if it's merely a projection, like a movie screen flickering with the illusion of depth? The holographic principle turns this idea on its head, suggesting that everything we perceive, every galaxy, every atom, even the passage of time, might be encoded on a distant two-dimensional surface, with black holes acting as cosmic pixels in this grand display. Think of a credit card hologram, those shimmering images that seem to float in midair. Tilt it one way and you see a 3D eagle. Tilt it another and it morphs into a globe. Now imagine the entire universe works like that. The stars above you, the ground beneath your feet, even your own thoughts. All of it could be information etched onto some unimaginable boundary, with black holes serving as the densest clusters of data. Leonard Susskind and Gerard T. Hooft first proposed this radical idea to solve the black hole information paradox, but the implications stretch far beyond astrophysics. If true, it means the solid, tangible world we experience is a kind of quantum mirage, a high-resolution rendering of underlying code. The math behind this is eerily precise. Just as a hologram can reconstruct a 3D image from 2D interference patterns, the equations of quantum gravity suggest that the universe's entire contents, every particle, every force, could be described by bits of information living on its outer edge. Black holes, with their event horizons acting like natural hard drives, fit perfectly into this framework. Their surfaces appear to hold exactly enough information to account for everything inside them, as if the volume of space we perceive is just a shadow of the data stored on its boundary. It's like discovering that every book in a library is actually just a different arrangement of ink on the front door. The rest is an illusion. This raises a haunting question. If spacetime is emergent, not fundamental, what's really running the simulation? Some theorists, like Juan Maldacena, have constructed exact mathematical models where a lower dimensional world without gravity perfectly describes a higher dimensional one with gravity, like a cosmic cheat code. String theory takes it further, suggesting that the strings vibrating at reality's core might be threads of information woven into a holographic tapestry. Even the Big Bang could be reinterpreted not as the birth of space and time, but as the moment this cosmic projector flickered to life. Yet the most unsettling implication isn't about physics, it's about perception. If the holographic principle holds, then free will, consciousness, even the passage of time might be secondary effects, like the glow of a screen rather than the light bulb itself. The present moment, with its vivid sense of now, could be an artifact of how the universe renders its data. Black holes, then, aren't just objects, they're reminders that reality might be far stranger, far more malleable than we ever dared to dream. And if that's true, then every time we gaze at the night sky, we're not just looking at stars, we're reading the universe's source code, pixel by pixel. Time crystals sound like something straight out of science fiction structures that repeat not in space, but in time itself, forever cycling without energy input. Nobel laureate Frank Wilczek first proposed these exotic quantum states in 2012, and they've since been created in labs using ultra-cold atoms and lasers. But the real cosmic stage for time crystals might not be a laboratory. It could be the chaotic depths of a black hole. Inside a black hole's event horizon, where gravity warps spacetime beyond recognition, the conditions are perfect for time crystals to form naturally. Imagine a clock that ticks forever without winding, its gears turning in perfect rhythm even as the universe decays around it. That's the essence of a time crystal, a quantum system locked in an eternal loop, immune to entropy's relentless pull. Near a singularity where time itself fractures into uncertainty, these loops could become the universe's most stubborn rebels, oscillating endlessly in the void. The implications for black holes are profound. Event horizons appear frozen from an outsider's perspective. A star falling in seems to slow, then stop as time grinds to a near halt. But what if that illusion masks a hidden reality? Time crystals could explain how quantum information persists despite the apparent freeze, their rhythmic patterns preserving data like a cosmic backup drive. It's as if the black hole's interior is a phonograph record, with time crystals as the needle, endlessly replaying the universe's song even as the record seems motionless to distant observers. This isn't just theoretical whimsy. Recent simulations suggest black holes might generate time crystals through their extreme gravitational shear, twisting quantum fields into self-sustaining loops. If true, it would mean these cosmic monsters aren't just tombs they're timekeepers, their depths humming with quantum metronomes that tick long after the stars burn out. The paradox of the frozen horizon would unravel, replaced by a deeper truth. Time doesn't stop at the edge of a black hole, it dances, and here's the most tantalizing possibility. If time crystals exist inside black holes, they might be the universe's way of cheating entropy, preserving information in cycles that outlast the cosmos itself. While everything else crumbles into heat death, these quantum loops could endure, whispering the secrets of long-dead stars into the infinite future. The next time you picture a black hole, don't imagine a static abyss, picture a clockwork heart, beating in the dark, keeping time for a reality we're only beginning to understand. When two black holes spiral toward collision, their final moments might not play out like a cosmic car crash, but more like a quantum magic trick. As their event horizons stretch and warp, the singularities at their cores could enter a state of superposition, neither fully merged nor separate, flickering between possibilities until the last instant. This isn't just theoretical poetry. Hidden within the gravitational waves, LIGO detects those ripples in spacetime from black hole mergers. There could be subtle tremors, faint stutters in the signal that betray this quantum hesitation. Picture two dancers spinning toward each other, their movements perfectly synchronized. Just before they touch, they freeze, not in one pose, but in all possible poses at once, a blur of potentialities. That's what might happen when black holes merge. Their singularities, those points of infinite density, resist settling into a single outcome until the universe forces their hand. The gravitational waves we detect could carry echoes of this quantum indecision, tiny deviations from the smooth, classical merger Einstein's relativity predicts. It's as if spacetime itself stutters, unsure how to resolve the paradox. The stakes couldn't be higher. If these anomalies exist, they'd be the first direct evidence of quantum gravity, a fleeting moment where the rules of the very small and the very large collide in plain sight. LIGO detectors, fine-tuned to catch spacetime's faintest whispers, might already have recorded these quantum hiccups without us realizing it. Some theorists, like Vitor Cardoso, suggest looking for echoes in the gravitational wave data, repeating patterns that could signal a superposition state snapping into place. Others propose that the final ring-down phase of a merger, where the new black hole settles into equilibrium, might vibrate at unexpected frequencies, like a bell tolling in two keys at once. But here's the twist: confirming this wouldn't just validate quantum gravity. It would rewrite our understanding of information itself. If black holes can merge while their singularities remain in superposition, then information isn't just preserved, it's entangled across multiple realities until the last possible moment. The universe, it seems, hates making definitive choices. Even in the most violent cosmic events, it keeps its options open, dancing on the edge of possibility until the final note rings out. The next time LIGO catches a black hole merger, listen closely. Beneath the thunderous crash of spacetime, there might be a quieter, stranger sound. The universe humming a quantum tune, a reminder that even in destruction, nothing is ever as simple as it seems. The firewall paradox is one of the most unsettling ideas in modern physics. What if the event horizon of a black hole isn't an invisible threshold, but a blazing wall of destruction? According to quantum mechanics, empty space isn't truly empty. It crackles with virtual particles popping in and out of existence. At a black hole's edge, these particles can split. One falls in while the other escapes as Hawking radiation. But here's the catch: this process should create an unimaginable firewall of energy, incinerating anything that crosses. Astronauts wouldn't just be stretched by gravity, they'd be vaporized in an instant. Yet this contradicts Einstein's relativity, which insists the horizon should feel like nothing special to someone falling through. So who's right? The answer might lie in quantum superposition's sleight of hand. Imagine a tightrope walker balanced perfectly between two futures, one where they fall left, one where they fall right. Now replace the tightrope with an event horizon and the walker with a particle. Superposition suggests particles don't have to choose between falling in or escaping. They can hover in both states at once, blurring the boundary between inside and outside. This quantum ambiguity could neutralize the firewall's fury. Instead of a wall of flame, the horizon becomes a shimmering veil of probabilities, where particles exist in a delicate dance of both rather than either or. It's as if the universe installed a quantum failsafe, preventing the paradox from ever triggering in the first place. This reshapes our understanding of black hole boundaries entirely. The horizon might not be a physical barrier at all, but a statistical illusion, like a mirage that only solidifies when you look too closely. Just as a spinning fan's blades blur into a solid disk, the firewall could be an artifact of how we observe quantum systems. From afar, the math suggests a lethal inferno, but for an astronaut falling in, superposition smooths the transition, making the horror vanish like a shadow under light. Some theories even propose that the firewall exists only for certain observers, a cosmic version of Schrödinger's cat where the horizon is both deadly and harmless until measured. The implications ripple beyond black holes. If superposition can resolve the firewall paradox, it hints at a deeper truth, that reality itself might be far more negotiable than we thought. The universe seems to have a knack for avoiding paradoxes not by brute force, but through quantum loopholes, rewriting its own rules on the fly. So the next time you picture a black hole, don't imagine a curtain of fire. Picture a quantum tightrope where every particle walks the line between destruction and escape, and in that balance, the universe finds a way to keep the peace. The event horizon of a black hole is supposed to be a one-way street, a point of no return where even light surrenders to gravity's grip. But quantum mechanics has a way of bending the rules, or rather, rewriting them entirely. Deep in the chaotic swirl of particles at the edge of a black hole, something extraordinary happens. Particles that should be trapped forever occasionally escape. Not by breaking free through sheer force, but by vanishing from one side of the horizon and reappearing on the other, as if slipping through a hidden backdoor in space-time. This is quantum tunneling, and it might be the universe's greatest disappearing act. Picture a ball rolling up a hill. Classical physics says if it doesn't have enough energy, it'll roll back down, no exceptions. But in the quantum world, there's always a chance, however small, that the ball will suddenly find itself on the other side of the hill, as if it teleported. That's tunneling in action. Near a black hole's event horizon, particles can pull off the same trick, bypassing the insurmountable barrier of gravity through sheer quantum stubbornness. It's not a steady leak. It's a probabilistic whisper, a cosmic game of chance where every now and then a particle beats the odds. What makes this even wilder is that tunneling might not just be a quirky side effect, it could be a fundamental feature of how black holes interact with the universe. Some theories suggest that Hawking radiation, the faint glow of particles escaping black holes, isn't just produced at the horizon but amplified by tunneling. Imagine a prison where the walls aren't solid, they're more like fog, and every so often a prisoner phases right through. The result, black holes might be far leakier than we thought, their infamous, inescapable nature more of a statistical average than an ironclad law. This could solve a long-standing mystery. Astronomers have detected strange radiation signatures near black holes that don't quite match predictions. If tunneling is at play, those anomalies might not be errors. They could be clues. The universe might be hinting that black holes aren't just sinks for matter and energy, but participants in a grander quantum exchange, where information and particles slip back and forth across the horizon in ways we're only beginning to decode. The implications ripple beyond astrophysics. If tunneling allows black holes to communicate with the outside universe, even minimally, it challenges our notions of cosmic isolation. Nothing truly gets sealed away forever, not even in the heart of a black hole. And if that's true, then the universe might have built-in escape hatches, subtle loopholes ensuring that no corner of reality is ever completely cut off. It's as if spacetime itself refuses to accept absolute endings, always leaving a door cracked open, however slightly, to the unexpected. Quantum entanglement already defies common sense particles linked across vast distances, instantly influencing each other no matter how far apart. But black holes take this spooky phenomenon and crank it up to cosmic extremes. Imagine performing a quantum experiment where one entangled particle falls into a black hole while its partner remains outside. The rules of quantum mechanics insist their connection should persist, but gravity this strong warps the very fabric of causality. Does the bond snap? Does it stretch, or does it twist into something entirely new? Black holes might be the ultimate testing ground for quantum theory, pushing entanglement beyond anything we can replicate on Earth. Laboratories here can only probe entanglement in relatively tame conditions across rooms, cities, even between satellites. But near a black hole's event horizon, spacetime contorts so severely that the concept of distance loses meaning. If quantum mechanics survives here, it suggests entanglement isn't just a quirk of particles. It's woven into the universe's foundation, unshaken by even the most extreme gravity. Conversely, if the connection frays or distorts, it could reveal cracks in quantum theory, hinting at deeper laws waiting to be discovered. This is why physicists like Leonard Susskind argue black holes are nature's most ruthless referees, stress-testing quantum rules in environments no lab could ever simulate. The stakes are higher than just theoretical curiosity. If entanglement withstands a black hole's gravity, it might mean the universe is far more interconnected than we imagined, with quantum links threading through warped spacetime like unbreakable threads. Some models even suggest black holes could store entanglement, acting as cosmic batteries that preserve these ghostly connections long after their original particles have vanished. Picture a relay race where the baton isn't passed but teleported. with black holes as the invisible runners keeping the quantum chain intact. Yet the wildest possibility isn't just survival, it's transformation. Black holes might not break entanglement but amplify it, twisting it into new forms we've never seen. Just as extreme pressure turns carbon into diamonds, a black hole's gravity could forge exotic states of quantum correlation, revealing phenomena like wormhole entanglement, where linked particles are connected by microscopic bridges in spacetime. These aren't just theoretical toys, they could be the key to understanding how information escapes black holes, or how the universe itself maintains coherence across billions of light years. So the next time you hear about quantum entanglement, remember, the real magic isn't happening in labs. It's playing out at the edge of black holes, where the universe conducts its most audacious experiments, and we're just beginning to decode the results. Black holes don't just spin, they might spin in every possible way at once. Imagine a cosmic top that doesn't settle into a single rotation, but exists in a blur of probabilities, wobbling between countless orientations simultaneously. This isn't just theoretical whimsy. Quantum superposition could mean a black hole's angular momentum isn't a fixed value but a spectrum of possibilities, flickering between states like a celestial strobe light. And this quantum spin chaos might solve one of astrophysics' most stubborn mysteries: why quasars and active galaxies shoot out jets of energy in such unpredictable, erratic bursts. Take the quasar 3C273 for example. From Earth, it appears to fire off jets in sudden, uneven pulses like a lighthouse with a flickering bulb. Classical physics struggles to explain this volatility, but quantum spin superposition offers a tantalizing clue. If the black hole powering the quasar isn't spinning in a single, stable direction, but exists in multiple rotational states at once, its magnetic fields and accretion disk would churn in a frenzy of probabilistic turbulence. One moment, the black hole's spin aligns to fling matter outward in a jet. The next, it superimposes into a different state, collapsing the jet like a hose with a kink. The result, the chaotic fireworks we observe across the universe. The math behind this is as elegant as it is bizarre. Just as electrons inhabit probabilistic clouds around atoms, a black hole's spin could occupy a cloud of possible angular momenta, its rotation smeared across quantum uncertainty. Observations of polarized light from quasars' light, whose waves align in specific patterns, hint at this very phenomenon. The polarization angles sometimes twist in ways that suggest the black hole's magnetic field, tied to its spin, is flipping between configurations. It's as if we're catching glimpses of a quantum roulette wheel in action, with spacetime itself as the ball. But here's where it gets even wilder. If black hole spins exist in superposition, they might not just explain erratic jets, they could be powering them. Each rotational state transition could release bursts of energy, like a cosmic gear shifting unpredictably. Some theorists propose these quantum spin flips might even generate fast radio bursts, those mysterious millisecond flashes of energy detected across the cosmos. Picture a spinning magnet suddenly reversing polarity, unleashing a shockwave. Now scale that up to a black hole's monstrous gravity, and you've got a recipe for cosmic fireworks. The implications stretch beyond astrophysics. If spin superposition is real, it means black holes aren't just massive objects, they're quantum kaleidoscopes. Their rotations a dynamic interplay of possibilities. Future telescopes, like the Event Horizon Telescope's next-generation upgrades, might spot the fingerprints of this quantum spin dance in the subtle warping of light around black hole shadows. And if they do, it'll be proof that even the universe's most violent engines are governed by the same quantum rules that dictate the behavior of the smallest particles. A spinning top in a child's hand and a supermassive black hole at the galaxy's core, both bound by the strange, shimmering logic of superposition. The quantum vacuum isn't empty, it's a seething ocean of potential, where particles flicker in and out of existence so quickly they're barely a whisper against the fabric of reality. These virtual particles usually vanish without a trace, their fleeting lives cancelled out in an instant. But near a black hole's event horizon, the rules change. Here, gravity's immense pull can rip these quantum ghosts apart, separating them before they can annihilate each other. One particle falls into the abyss, while its partner escapes as Hawking radiation, a process that slowly drains the black hole's energy over eons. Yet superposition adds a layer of profound strangeness. Until measured, these particles exist in a twilight state, neither fully real nor entirely illusory, dancing on the edge of existence itself. This quantum tightrope walk reshapes our understanding of thermodynamics, the science of heat, energy, and entropy. Normally, energy conservation is ironclad. What goes in must balance what comes out. But virtual particles near a black hole defy this expectation. They borrow energy from spacetime itself, a cosmic loan that only gets repaid when one particle escapes. It's as if the universe runs on quantum credit, with black holes acting as both debtors and creditors in a grand thermodynamic ledger. The kicker, superposition, means the books might never fully balance. Until an observer measures the escaping particle, the system exists in a probabilistic haze where energy fluctuates between real and imaginary like a fever dream of physics. The implications ripple far beyond black holes. If reality itself can blur the line between existence and illusion at the quantum level, what does that mean for the fundamental laws we take for granted? Thermodynamics has always been about certainty, the inevitable march toward disorder. But superposition introduces a wild card, a loophole where the universe might temporarily sidestep its own rules. Picture a magician's trick where the coin isn't just hidden, it's simultaneously in the hand and the pocket until the audience looks. Black holes perform this sleight of hand on a cosmic scale, with virtual particles as their quantum coins. Even stranger, this process might explain why black holes appear to have temperature, a concept that baffled physicists when Hawking first proposed it. How can something that devours light and matter radiate heat? The answer lies in the chaotic quantum froth at the horizon, where virtual particles constantly emerge and vanish. Superposition ensures this froth isn't just random noise but a finely tuned thermodynamic engine, converting gravitational energy into radiation with eerie precision. It's as if the black hole's surface is a quantum stovetop, simmering with probabilities that only resolve into real particles when the universe demands it. The real magic, though, is how this ties into information. If virtual particles carry away energy, do they also carry away data about what fell into the black hole? Some theories suggest the answer is yes, that Hawking radiation isn't just random noise but a scrambled quantum message, a cosmic SOS broadcast from the edge of oblivion. Superposition ensures this message isn't lost in transit but preserved in the delicate interplay between what's real and what's potential. The universe, it seems, has a way of keeping receipts even in the most extreme conditions imaginable. So the next time you hear that black holes are simple destroyers, remember, they're also alchemists turning the quantum vacuum's fleeting whispers into something tangible. And in that transformation, they reveal a truth far stranger than fiction, that existence itself might be the universe's most audacious magic trick, with superposition as its sleight of hand. Quantum mechanics already plays tricks with time-delayed choice experiments, show that observing a particle now can seemingly alter its path in the past. But near a black hole's singularity, where gravity warps spacetime beyond recognition, this quantum retroactivity might scale up to cosmic proportions. Imagine a cosmic editor with an undo button, rewriting events that technically already happened. Black holes, with their extreme environments, could be twisting causality into knots, erasing and reconfiguring their own histories in real time. Take the quantum eraser experiment, a classic demonstration where measuring or erasing information about a particle's path changes whether it behaved like a wave or a particle in the past. Now amplify that effect near a singularity, where spacetime itself becomes a quantum foam of probabilities. A black hole's gravitational chaos might act like a universal eraser, scrambling information in ways that retroactively tweak the fabric of reality. It's as if the universe keeps multiple drafts of events, and black holes are flipping between them, selecting versions of history that align with their ever-shifting quantum states. The implications for causality are mind-bending. Normally, the past is set in stone, a bullet fired can't return to the gun. But near a singularity, quantum erasure could blur that certainty. Particles falling in might not just disappear, they could retroactively alter the conditions under which they were swallowed, like a snake eating its own tail in reverse. Some theories, like post-selection in quantum mechanics, suggest black holes might choose histories that avoid paradoxes, self-correcting their timelines in ways that appear seamless to outside observers. Picture a film reel where frames aren't fixed, they're fluid, adjusting dynamically to maintain a coherent story. This isn't just theoretical sleight of hand. If black holes rewrite their pasts, it could explain why certain gravitational wave signals from mergers appear oddly clean, as if the universe smoothed out inconsistencies before we could detect them. The chaotic aftermath of a collision might contain subtle fingerprints of retroactive editing, like faint echoes of alternate timelines collapsing into one. Future observatories, like the next-generation LIGO or space-based detectors, could hunt for these anomalies, statistical glitches in the data that hint at causality bending under extreme quantum strain. Yet the wildest possibility isn't just about black holes, it's about us. If quantum erasure operates on cosmic scales, could the universe itself be a dynamic manuscript with singularities as its editors? Every time a black hole swallows matter, it might not just be consuming energy, it could be refining the narrative of spacetime, pruning paradoxes, and stitching together a consistent, if flexible, reality. The past, in other words, might not be as fixed as we think, and if that's true, then black holes aren't just gravitational monsters. They're the universe's archivists, quietly redacting and revising the cosmic story as it unfolds. A black hole is both a cosmic shredder and a quantum librarian, depending on who's watching. This bizarre duality, known as black hole complementarity, suggests reality itself fractures at the event horizon, splitting into multiple, equally valid truths. Leonard Suskind's revolutionary idea appends everything we thought we knew about these gravitational beasts. To an astronaut plunging in, the horizon might be a harmless threshold, a silent gateway to oblivion. But to a distant observer, that same horizon could blaze with lethal fire, incinerating anything that approaches. Both perspectives are correct, neither is the whole story. Think of light's famous wave-particle duality. Photons act like spread-out waves until you measure them, then snap into sharp, localized points. Black holes take this quantum weirdness and blow it up to cosmic proportions. The event horizon isn't just a physical boundary, it's a quantum Rorschach test, revealing different truths to different observers. A particle falling in might experience smooth, uneventful spacetime, while its entangled partner, hovering outside, sees that same particle smeared across a searing firewall. It's as if the universe runs two conflicting simulations simultaneously, refusing to pick a single version of events. This isn't just philosophical hand-waving. Complementarity solves the infamous Firewall paradox, which had physicists at war for years. If Hawking radiation carries information out of a black hole, quantum mechanics demands that the horizon must be a violent inferno to preserve causality. But Einstein's relativity insists it should feel like empty space to a falling observer. The contradiction seemed irreconcilable until Susskind realized both can be true. The horror of the firewall and the serenity of the void aren't mutually exclusive. They're two faces of the same quantum coin, forever locked in superposition until an observer forces a choice. The implications ripple far beyond black holes. If reality is observer-dependent at the horizon, could the same principle apply elsewhere? Some interpretations of quantum mechanics already suggest that measurement shapes reality, that particles exist in blurred probabilities until observed. Black hole complementarity takes this idea and cranks it to extremes, implying that the universe might stitch together conflicting truths into a cohesive whole through sheer quantum stubbornness. It's as if spacetime itself runs on democratic principles, allowing every observer their own valid perspective while hiding the contradictions behind an event horizon's veil. This cosmic democracy comes with a catch, though. Observers can't compare notes across the horizon. No signal can escape the black hole's grip. This cosmic censorship ensures the paradoxes stay hidden, like parallel worlds forever separated by an unbridgeable gap. Yet the mere possibility reshapes how we think about information, causality, and even the nature of existence. If black holes can harbor multiple truths without imploding, perhaps reality itself is far more flexible than we ever imagined, a tapestry of perspectives woven together by quantum threads, where the only absolute is that nothing is absolute at all. Black holes are the ultimate heavyweights of the cosmos, or are they? What if their immense mass isn't a fixed, crushing certainty, but a quantum roll of the dice? Imagine stepping onto a scale that doesn't settle on one number but flickers between possible weights, never committing until you look. That's the startling possibility emerging from quantum gravity research, that black holes might not have definite masses at all, but exist in a shimmering superposition of possibilities, hovering between different gravitational identities until the universe forces a choice. This isn't just theoretical whimsy. Astronomers have long noticed odd discrepancies in black hole mass measurements, especially in merging pairs detected by gravitational wave observatories like LIGO. Some collisions seem to produce remnants slightly lighter than expected, as if part of the black hole's mass temporarily opted out of the equation. Quantum superposition offers a compelling explanation. The black holes involved weren't in a single mass state during the merger, but a blend of probabilities. Picture two boxers stepping into a ring where their weight classes fluctuate mid-fight, their punches landing with unpredictable force depending on which quantum version of themselves throws them. The implications for gravitational wave astronomy are profound. If black hole masses exist in superposition, their mergers wouldn't produce clean, singular signals. They'd generate subtle interference patterns, like overlapping ripples from stones tossed into a pond at slightly different times. Future detectors, like the space-based LISA mission, might catch these quantum fingerprints in the form of faint echoes or frequency shifts buried in the data. It would be like hearing a symphony where some notes are played by invisible instruments, their presence felt but not seen. But here's where it gets even stranger. If mass can exist in superposition, then gravity itself, the force that shapes the cosmos, might be fundamentally probabilistic. A black hole's event horizon could flicker between sizes, its gravitational pull waxing and waning like a tide governed by quantum chance. This would mean spacetime isn't just warped by mass, it's warped by the potential for mass, a cosmic house of mirrors where even the most basic properties refuse to settle down. The philosophical ramifications are dizzying. If a black hole's mass isn't real until measured, what does that say about the nature of reality itself? Are other cosmic properties a star's luminosity, a galaxy's spin also hovering in quantum limbo? It's as if the universe runs on placeholder values, only filling in the details when absolutely necessary. And if that's true, then every time we measure a black hole's mass, we're not just observing it, we're participating in a cosmic decision, forcing the universe to pick a number from its quantum hat. So the next time you picture a black hole, don't imagine a static, singular monster. Picture a quantum chameleon, its weight flickering between possibilities, its gravity a spectrum rather than a certainty. And somewhere in that uncertainty lies a clue not just to how black holes work, but to how the universe itself balances its books, one probabilistic tick of the scale at a time. Black holes might be the universe's ultimate IT department, silent, unseen, but tirelessly working behind the scenes to patch up quantum errors before they crash the cosmic system. Think about how your phone autocorrects typos before you hit send, or how computer memory has built-in redundancy to fix glitches. Now imagine that same principle scaled up to astrophysical proportions, where black holes aren't just gravitational monsters but sophisticated quantum error-correcting machines. The idea sounds like science fiction, but the math is shockingly precise. The chaotic turbulence at a black hole's event horizon could act like a cosmic checksum, detecting and repairing corrupted quantum information before it spreads. Here's how it might work. Quantum data is notoriously fragile. A single disturbance can scramble the delicate superpositions that power quantum computing. Yet black holes, with their extreme conditions, seem to preserve information against all odds. The holographic principle suggests this isn't an accident. Just as error-correcting codes in computers use redundancy to recover lost data, a black hole's event horizon might encode duplicate copies of quantum states in its swirling quantum foam. When a particle's information risks being lost, say, by falling into the singularity, the horizon's chaotic dynamics could rewrite the data onto escaping Hawking radiation, like a cosmic control plus Z undoing deletion. It's as if the universe has a fail-safe protocol with black holes as its enforcers. This isn't just theoretical elegance. Lab experiments with quantum computers already rely on error correction to maintain coherence, using entangled particles to flag and fix mistakes. Black holes could be nature's version of this a-billion-year-old system for stabilizing quantum information against the ravages of entropy. Leonard Susskind and others have even drawn parallels between black hole physics and quantum error-correcting codes like the surface code, where information is stored non-locally, making it resilient to local disruptions. Picture a hard drive that doesn't just back up files but scatters them across its surface in a way that even if half the drive melts, the data survives. That's the kind of robustness black holes might offer the cosmos, but here's the twist. If black holes are cosmic debuggers, they're not just fixing errors, they're generating them too. The same quantum turbulence that corrects glitches also creates new ones, like a self-updating operating system that occasionally crashes while patching bugs. This duality could explain why black holes seem to both preserve and scramble information, a paradox that's baffled physicists for decades. They're not just erasing the cosmic whiteboard, they're erasing and rewriting it simultaneously, in a loop of destruction and repair that keeps the universe running smoothly. Imagine the implications. If the cosmos truly self-corrects through black holes, It suggests an underlying order to the chaos, a hidden logic that's been running since the first stars collapsed. Dark energy, the expansion of the universe, even the arrow of time might all be side effects of this quantum maintenance. It's a humbling thought that the same forces tearing spacetime apart are also quietly stitching it back together, ensuring the cosmic program never fully crashes. And if we could decode their algorithms, we might finally understand how reality itself stays so improbably stable, even in the face of entropy's relentless tide. Roger Penrose's cosmic censorship conjecture has long been the universe's ultimate spoiler alert, a rule that singularities, those points of infinite density where physics breaks down, must always be hidden behind event horizons. No peeking, no exceptions. It's nature's way of keeping its most terrifying secrets under wraps. But quantum superposition doesn't play by classical rules. What if, in fleeting probabilistic flashes, the cosmic veil slips just enough to let a singularity bare its teeth to the universe? Picture a prison with walls so thick, no light or sound can escape. Now imagine those walls flickering in and out of existence like a faulty hologram. For brief, unpredictable moments, the prisoner inside becomes visible, not fully, not clearly, but just enough to catch a glimpse of something that shouldn't be seen. That's the nightmare scenario cosmic censorship was designed to prevent. Yet quantum mechanics thrives on violating the forbidden. Near a black hole's dying moments or during violent collisions, the event horizon might thin to a quantum whisper, its certainty dissolving into a haze of probabilities. In those instants, a singularity could go naked, exposing the raw underbelly of spacetime itself. This isn't just theoretical rebellion. Certain solutions to Einstein's equations, like the Kerr-Newman metric for spinning charged black holes, already flirt with naked singularities under precise conditions. Normally, these are dismissed as mathematical oddities, cosmic glitches the universe would never allow. But superposition changes the game. If an event horizon exists in multiple states at once, sometimes thick, sometimes thin, then the singularity's exposure isn't a yes or no question. It's a spectrum, a quantum roulette wheel where every spin offers a chance, however tiny, for the universe's best-kept secret to slip out. The implications are staggering. A naked singularity wouldn't just defy Penrose's conjecture, it would rewrite the rules of causality. Without an event horizon to shield it, the singularity's infinite curvature could send shockwaves through spacetime, bending light into knots and scrambling the arrow of time. Nearby observers might witness events where cause and effect trade places, where gravity becomes so unpredictable that even quantum fields fracture into chaos. It would be like staring into a cosmic funhouse mirror where every law of physics distorts beyond recognition. Yet the true revelation might lie in what these flashes reveal about the universe's deepest fabric. Singularities aren't just in points, they're portals to whatever lies beyond our current physics. String theory suggests they might be tangled fuzzballs of vibrating strings. Loop quantum gravity imagines them as quantum bounce points. If superposition lets us glimpse them, even probabilistically, it could be like finding a crack in reality's foundation, one that lets in just enough light to hint at what's really holding everything together. The catch, these quantum violations of cosmic censorship would be vanishingly rare, flickering into existence for fractions of a second before spacetime slams the door shut. Detecting them would require instruments sensitive enough to catch gravity's faintest whispers, perhaps next-generation gravitational wave observatories or quantum-enhanced telescopes. But if we ever do, it won't just be a breakthrough. It'll be the universe's ultimate taboo, broken in a flash of quantum audacity. And in that flash, we might finally see what lies beyond the edge of the known. Black holes might not just be cosmic dead ends, they could be delivery rooms for entirely new universes. Think of a quantum fluctuation not as a blip, but as a cosmic branching point where reality itself splits. In the seething quantum foam near a singularity, every fleeting superposition, every particle's unresolved maybe, could rip the fabric of spacetime wide open, birthing a fresh cosmos with its own unique laws. This isn't just wild speculation. The math of quantum gravity suggests that the extreme conditions inside a black hole don't merely crush matter. They stretch the very definition of existence, creating pockets where physics reboots with new rules. The many worlds interpretation of quantum mechanics already paints reality as an ever-growing tree of possibilities, where every quantum decision spawns parallel timelines. Now imagine black holes as the trunk of that tree, their singularities acting as cosmic routers, directing information into new branches of the multiverse. When a particle inside a black hole exists in superposition both here and there, both now and then, it isn't just uncertain, it's untethered, free to crystallize into entirely new realities. Picture a kaleidoscope shattering into infinite reflections, each shard a self-contained universe with its own version of history, its own constellations, its own you. This idea isn't without precedent. The theory of inflationary cosmology suggests our own universe may have sprouted from a quantum bubble in some primordial vacuum. Black holes could be running the same playbook on a smaller scale, their singularities acting as seeds for pocket universes. Lee Smollen's controversial cosmological natural selection hypothesis takes it further, proposing that each black hole births a universe slightly tweaked from its parent, with physical constants optimized to produce more black holes. Its evolution on a cosmic scale universes giving birth to universes, with black holes as the reproductive organs of the multiverse. The implications are dizzying. If every black hole is a potential universe factory, then the cosmos might be littered with the offspring of ancient singularities, each with its own unique physics. Some could be barren wastelands where gravity is too weak to form stars. Others might crackle with hypercharged forces, birthing civilizations we can't even imagine. And somewhere in that infinite ensemble, there's a universe where you made different choices, where every road not taken in this reality became someone else's destiny. But here's the twist: these baby universes aren't necessarily elsewhere. The holographic principle suggests they might exist within the black holes that spawn them, hidden behind event horizons like Russian dolls nested inside one another. An astronaut falling in wouldn't just be crushed, they'd be stretched across the birth pangs of a new cosmos, their atoms scattered into the primordial soup of another Big Bang. It's as if black holes aren't destroying information but repackaging it, recycling the raw materials of one universe into the building blocks of another. The most haunting possibility: we might already be inside one. If black holes birth universes, then our own cosmos could be the offspring of a singularity in some long-dead ancestor universe. The dark energy accelerating our expansion, the mysterious smoothness of the cosmic microwave background, these could be fingerprints of our celestial parent, quantum fluctuations frozen into our laws like genetic traits. The night sky wouldn't just be a window to deep space. It would be a mirror reflecting the turbulent womb of a black hole we'll never see. So the next time you gaze at a black hole simulation, remember, you might not be looking at a grave. You might be staring into a cradle, a quantum engine humming with the potential to spin reality into existence, one superposition at a time. And somewhere in that chaos, another version of you is staring back, wondering the same thing. Black holes aren't just defined by their mass and spin, they can carry an electric charge, a lurking voltage hidden beneath their event horizons. But what if that charge isn't a fixed value, flickering between positive and negative like a cosmic coin toss? Quantum superposition could mean a black hole's electromagnetic identity is unresolved, its charge existing in multiple states simultaneously. Picture a thunderstorm where every cloud is both positively and negatively charged at once, crackling with indecision. Near the event horizon, this quantum ambiguity might spark lightning bolts of pure paradox, arcing across spacetime in ways that defy classical physics. The math behind this is as elegant as it is bizarre. Just as electrons in an atom occupy probabilistic clouds rather than fixed orbits, a black hole's charge could smear across a spectrum of possibilities, its electric field fluctuating like a mirage. These aren't minor tweaks, they're seismic shifts in how black holes interact with their surroundings. Normally, charged black holes, known as Reissner-Nordström or Kerr-Newman black holes, create orderly electromagnetic fields. But introduce superposition, and those fields become quantum roller coasters, twisting and realigning unpredictably. Magnetic lines might knot themselves into braids, while electric discharges flicker in and out of existence, vanishing before they can fully form. This could solve an astrophysical puzzle, the origin of fast radio bursts, those millisecond blasts of energy that light up telescopes across the universe. Traditional explanations point to colliding neutron stars or magnetars, but some bursts defy these models, their patterns too erratic, their energies too extreme. A superposition-charged black hole offers a compelling alternative. Imagine the event horizon as a quantum capacitor, building up charge in probabilistic leaps rather than steady increments. When the superposition finally collapses triggered by infalling matter or quantum fluctuations, it unleashes a storm of electromagnetic energy, firing off radio waves like a cosmic Morse code. The evidence might already be hiding in plain sight. Telescopes have detected strange, repeating radio bursts from regions near suspected black holes, their signatures unlike anything produced by known stellar objects. Some pulses arrive in clusters, as if something is flickering between states, while others show bizarre polarization patterns, light waves twisted in ways that suggest magnetic fields gone haywire. If these are the fingerprints of quantum charge superposition, they'd resemble static from a radio tuned between stations, catching glimpses of multiple realities at once. But the wildest implication isn't just about radiation, it's about time. A charged black hole's electric field warps spacetime differently than gravity alone. In superposition, this could create pockets where time stutters, looping back on itself in tiny, quantum-sized knots. Lightning near the horizon might strike in reverse. Magnetic fields could oscillate between future and past configurations. It's as if the black hole's charge uncertainty infects causality itself, turning the event horizon into a hall of mirrors where cause and effect blur. If proven, this would revolutionize how we classify black holes. No longer just gravitational heavyweights, they'd be electromagnetic chameleons, their quantum charge states as fundamental to their identity as their mass or spin. Future telescopes, like the Square Kilometre Array, could hunt for the telltale static of superposition in deep space radio signals, while quantum simulations might recreate these extreme conditions in labs. Until then, every mysterious burst from the cosmos whispers the same tantalizing question. Are we hearing the universe's most charged debate, playing out in real time at the edge of a black hole's uncertainty? Black holes might not die, they could be reborn. When Stephen Hawking first predicted that black holes slowly evaporate through quantum radiation, it seemed like the ultimate cosmic dead end. But hidden in that process is a twist stranger than fiction. As a black hole shrinks to its final moments, its quantum information, those scrambled superpositions and entangled states, doesn't just disappear. It might redistribute across space-time like seeds scattered in the wind, each carrying the potential to sprout new black holes elsewhere in the cosmos. The universe, it seems, has a recycling program, and black holes are its tireless custodians. Picture a dying star collapsing into a black hole, a process we've long thought of as a one-way trip. Now imagine that black hole, billions of years later, radiating away its mass until it's nearly gone. At the quantum level, its final moments could resemble a cosmic pressure cooker, where the extreme energy density sparks new fluctuations in the fabric of spacetime. These aren't just random blips, they're echoes of the original black hole's quantum structure, carrying fragments of its information into the void. Like a phoenix reduced to embers, those embers might still glow hot enough to ignite new fires elsewhere. This isn't just poetic symmetry, it's a potential solution to one of physics' greatest puzzles, the fate of information in an evaporating black hole. If quantum states aren't destroyed but scattered, the universe could be weaving an endless tapestry of creation and destruction. Every black hole's demise might plant the seeds for its successors, birthing new singularities in a cycle as old as time itself. Some theories, like loop quantum gravity, even suggest these rebirths could happen in regions of spacetime far removed from the original black hole, as if the cosmos is playing a game of quantum teleportation with its own building blocks. The implications stretch beyond astrophysics. If black holes recycle quantum information, the universe might not be evolving toward heat death, a cold, lifeless equilibrium, but cycling through phases of activity and renewal. Dark energies accelerating expansion, the mysterious smoothness of the cosmic microwave background, even the distribution of galaxies could all be fingerprints of this grand recycling program. It's as if the cosmos has built-in redundancy, ensuring that no quantum state is ever truly lost, just repurposed in ways we're only beginning to glimpse. Here's the most tantalizing possibility. This cycle might not be random. The way a dying star's collapse is governed by precise physics, the redistribution of a black hole's quantum information could follow hidden rules, a cosmic algorithm optimizing the birth of new singularities. Imagine the universe as a self-adjusting machine with black holes as its gears, grinding down reality only to spit it back out reshaped, refined, and ready to begin the dance anew. So the next time you hear that black holes are the universe's end game, think again. They might just be its way of hitting the reset button, ensuring that even in the coldest depths of space, something new is always stirring in the quantum dark. From information paradoxes to cosmic holograms, the marriage of quantum superposition and black holes reshapes our understanding of reality itself. These 30 unseen implications reveal a universe far stranger than Einstein or Bohr ever imagined. One where black holes are not just destroyers but creators, processors, and perhaps even portals. They blur the line between physics and philosophy, challenging us to rethink the very nature of existence. Consider this: every black hole might be a cosmic artisan, spinning raw quantum uncertainty into the fabric of new universes. Or a librarian encoding the history of everything it consumes onto the surface of its event horizon. Some could even be time travelers, bending causality into knots with their probabilistic spins. The more we learn, the clearer it becomes black holes aren't anomalies. They're the universe's way of stress testing its own rules, pushing the boundaries of what's possible. And we're just beginning to crack the code. Gravitational wave detectors like LIGO are eavesdropping on black hole collisions, catching whispers of quantum gravity in their ripples. Telescopes hunt for the faint glow of Hawking radiation, while theorists wrestle with equations that might one day unite relativity and quantum mechanics. Every discovery peels back another layer, revealing a cosmos more interconnected, more dynamic, and more mysterious than we ever dreamed. What's next? Maybe we'll find proof that black holes birth new realities, or that their singularities are gateways to other dimensions. Perhaps we'll harness their quantum tricks to build unhackable quantum networks, or even, dare we imagine, craft technologies that bend spacetime itself. The possibilities are as limitless as the superposition states hiding inside every singularity. So as we stand on the brink of these breakthroughs, remember, the final chapter of physics isn't just unwritten, it's being drafted in the quantum chaos at the heart of every black hole. If this journey through the quantum cosmos left you questioning everything, you're not alone. Hit like if your mind is officially blown, subscribe for more deep dives into the universe's wildest secrets, and drop a comment below. Which of these implications rocked your reality the most? Until next time, keep gazing at the stars and never stop wondering what's lurking just beyond the edge